modification of Stokes integral. So why modification is important for geodetermination? Let me draw the kernel, Stokes kernel. If I plot the Stokes kernel, Stokes over Stokes, it will have such a shape. For example, let's see up to degree 10. So if it is so, it means that I need the far zone data for integration or for performing the integral. But if I have limited data, not that long, not that far data, just close to the computation point, and I want to, for example, use up to 3 degree, 3 degree left, 3 degree right, then I would like to have this kernel like this. It means that the kernel decays or goes down fast, so that after degree 3, it is almost 0. When you integrate the data, and you have this kernel inside the integrand of the Stokes integral, you don't need to consider those values after those data which are far from the center point, which is here by 3 degrees. After 3 degrees, you can ignore them. So you see, for example, if this is the sphere and you have a cap size of integration, and I have already discussed about truncation, the effect of this part, but I want to determine a specific cap size, for example, 3 degrees. I just perform the integration inside this domain without thinking about the data outside. Like that. So in this case, because I have to change this kernel, change this integral a little bit, so that the effect of the data outside this integration domain is minimized. This change is called modification. Modification means to change the kernel of the integral or Stokes integral in such a way that the data outside the specified, that specific cap size that we have or integration area is minimized. So let me write the formula. So this is the geoid. Let me draw geoid. Then it is Stokes formula, and you know it very well now. Stokes function delta G gravity anomaly and epsilon. This is the original Stokes formula, and I want to modify this. I want to change the kernel. How do I do it? Let me call this L, which means that the modified kernel. I want to change this kernel. How I write the kernel, a Stokes kernel, minus another kernel. Let me call it from 0 up to L. This is degree of modification. We'll discuss that later. 2n plus 1 over 2 Sn p n cosine sine. This is modified kernel. This modification degree. If you remember from the previous discussion that we had, I showed you that the Stokes kernel has this spectral form. This one minus this term which comes here. I want just to compare one thing here. For a Stokes kernel, this is the spectrum, or in other word, this is the spectrum of the Stokes kernel, and this is the modification parameters of the kernel. Let me see right here. Modification parameters. So, what is happening? 2n plus 1 or 2 is related to this norm of this Pn. Is related to any spherical function. The only difference is this Sn here and 2 over 1. What does that mean? This means that I am changing the spectrum of the Stokes kernel. Or I can write, therefore, this Stokes function like in a spectral form like that. So, spectral form for this modified kernel, let me start from 2, will be 2n plus 1. This is related to Pn or any spherical function. We have 2n plus 1 minus Sn star. I will say later what is Sn star. Cosine psi. So, since Sn is limited up to degree n, I wanted to have infinity in my formula. Actually, I write this Sn like that. I say that, okay, Sn will be Sn when n is smaller than n, and 0 when is larger than n. So I have now the modified kernel in a spectral form. And what you see here is, in fact, modified spectrum. How it is modified? I subtract something from the kernel, Stokes kernel. So in this case, this kernel will be modified or will change the behavior. But how? We need a criteria for changing this behavior. We need, for example, to minimize the error, the truncation error of the Stokes integral. And we try to estimate these modification parameters in such a way that the truncation error will be minimized. So let me start again. Therefore, I will write it like that. N is R over 4 pi gamma SL delta G is sigma. But there is a problem here. Let me write it again in another way to explain it better. There's a problem here. I have written S psi minus, for example, to infinity, 2n plus 1 over 2 Sn, it was infinity, it's L, SL Pn cosine the sigma. Well, that formula is not actually a Stokes formula anymore because I have changed this kernel function. This is something else. As you see, I have removed something from the kernel. And then I remove this, I take the integration, then I have to restore this effect after integration. So what is the restoration step? So let me just look at this term only, not this Stokes. What is that term? I have removed this term, then I have to reduce it. How can I reduce it? I will write it, comma, and add from 2 to L to n plus 1 Sn Pn cosine psi delta G the sigma. So what do we see here? We see 2n plus 1, we have a 4 pi behind, and we have an integral, and we have delta G and the sigma. I hope you remember this formula. At delta Gn is 2n plus 1, 4 pi integral delta G Pn cosine. So that's the Laplace coefficients of the gravity anomaly. So that's it. Therefore, I can write that this formula will be R over, these two comes here, gamma is at the same place, summation remains from 2 to L, Sn will be there, and delta Gn. So that's the spectral form of this term. It means that when I remove this term from the kernel and perform the integration, since I have changed the kernel, I have to restore this term again to the integral. Otherwise, it will be wrong. So this means that I should write the formula for the geoid is like that. R over 4 pi gamma integral SL is modified kernel delta G ds sigma, prime for means that integration, plus the restore step, and not infinity, and delta G. So I have modified the kernel. I have written, remove, and restore. But the question is I have not limited this yet. Therefore, let me just focus on this part, the integral part. I write this integral in two ways. If you remember, it was like that. Integral 0, the cap of integration, SL psi delta G prime dsi plus R over 4 pi gamma. Here is the truncation part, the effect of Farzun data. So SL psi. So this one is the left one is the one that we need actually to use for integration, and we just limit the integration cap. That's fine. But the question is, if I have this S, how can I estimate this S? I will estimate this S in such a way that this term is minimized. How? The question is how. I need to write this term. Now it's a truncation. Truncation in a spectral form. Let me write it again. So, truncation. Let me write truncation by delta n. It's a truncation error for y gamma truncation. I will rewrite this formula. Psi. That's it. That's it. If you remember, I can define a function like that. I can say that it is 0 over the area when I have the cap size, integration size, and will be a modified kernel outside that cap size. I am going to do the truncation, compute the truncation error. So SL spar L will have this spectral form because it's a spherical function 2n plus 2, and I call it QNL. L because it is L modified up to degree L Pn cosine psi. So based on this definition, I can rewrite the truncation over the full sphere. I will write S bar L psi delta G d psi, and now I insert this equation inside here, and I come to delta m for pi gamma integral. Now the spectral form comes in 2 to L 2m plus 1 to QNL psi 0 Pn cosine psi delta G prime d psi. And again, we have 4 pi here, we have integral here, we have 2n plus 1 here, Pn cosine, and then I can write that this is delta Gn. Therefore, the spectral form, let me write it another color, of this truncation error will be 2 to L, because of this L, will be QNL sigma 0 delta G. That's it. That's the truncation error. Truncation error of modified Stokes formula. So that's the truncation error, but we have not still modified it. We have assumed that if I have one modification parameter like S, and I subtract it from the spectrum of the Stokes function, the kernel will be modified. Yes, and if it is modified, we will have this truncation. But what is that parameter? Then we have to estimate this. Let's see. I will rewrite this formula again. To L, QL, so this is Laplace coefficient of the modified kernel. So Laplace coefficient of modified kernel. So what does it mean? It means that Q and L is 2n plus 1 over 4 pi integral of SL psi Pn cosine S. And I already derived the spectral form of this function. Let me put it here in the spectral form. I will write that the spectral form in another color. Plus 1 minus plus Pn cosine. Now it should be Pn prime, the Pn cosine and the sigma. So if I consider the first one, I just consider this term, this first spectrum. I will come to this formula. If I simplify it, I will come to 0 up to psi, sine psi, the psi, minus, and for the second one, it will be 2m plus divided by 2, and integral, you will see we have summation m plus 2 is infinity 2m plus 1 over 2 Sn, and I do not have place, then I have to go up. I continue this part, this part above will be integral psi 0 up to infinity Pn cosine Pn prime cosine psi sinus psi. This formula will be this part. is known as pole coefficients. And there is recursive formula for computing that. This term will be nothing else than Qn that we have already discussed. Oh, sorry, should 0 top to pi. So it should be 1. So based on this, the QL psi will be truncation of the Stokes formula minus summation of 2m plus 1 n en n prime. It should be prime. N prime is 0. So that's the formula for the truncation of the modified Stokes formula, modified Stokes function. And now I come back to the error, which was R over 2 comma Q and L psi 0 delta G. If you remember, I can take the operator m from both sides, but I square them first. When I square them, and assuming that the degrees are not correlated, then the average operator, as I apply for this, will be 4 gamma 2 square, and here will be degree variance delta G square. Yes, degree variance. So this is the mean square error, and I want mean square error of the truncation error, the square error of truncation, and I want this to minimize, to be minimum. How do I do that? I take the derivative with respect to Sn parameters. If I take the derivative, it will be, this term is not important, I will ignore it. So I'll take the derivative, it will be m Q N L psi prime Q N L psi 0 m delta G n square. The square is to be inside is 0. This term has no effect, the multiplication, and here we have S parameters here and here, and 2 has no effect either. Therefore, I can write so if I take the derivative with respect to sk, for example, it will be 2k plus 1 over 2 sk will be 1, then e n and k psi 0, then I have this one qn psi 0 minus summation n to L 2k plus 1 2 and it's either R 2R plus 1 2R S R E N N R and R. So this term has no effect because it's 0. Therefore, this term should be 0 to have it. Therefore, I get a system of equations to solve. And 2k plus 1 to SR E k n psi 0 equals to kn. So it means that for each spectrum of the truncation error of Stokes formula, I will have a mathematical model. And by terms of the pole coefficient. Pole coefficients are noun. This truncation error is noun. We already have the formula for them. The only thing which is not noun is S. Then I can make a system of equation like this. R, for example, S most obvious equals to Q matrix, not Q truncation. And then S will be inverse of the Q. Then you solve these truncation coefficients. If you solve these truncation coefficients, then you simply insert it to the geoid estimator that in the beginning I presented. It was R for pi gamma integral over small cap. Now we have the modified kernel delta G sigma plus restore of the removed effect 2 degree L Sn delta G. So simply when you estimate this SR from this equation, this SR comes back to SL, it comes back to S. In this case, you shouldn't worry about the far zone data because the effect of far zone data has been reduced, or the truncation error of the integral has been reduced already, and the modification parameters have been estimated in such a way that this truncation error outside this integration cap is minimized. This method that I have applied here is known as Molodensky modification. There are many types of modifications, but the simplest one is this one, is the Molodensky. There are combination of Molodensky with another method which is known as Meissel method. This is least square modification that my professor has created. That one is much more advanced. But in all of them, the principle is that we change the spectrum of the Stokes kernel, create a new kernel which has concentration on the cap integration cap. Of course, they all restore the effect of this change. When you change this kernel function, what you get is not directly geoid because you have changed the kernel. You need to consider that change and put it back after computation. So you remove and modify the kernel, perform the integration, and restore the removed kernel, the removed part. Yeah. That's the whole principle for modification. And this S parameter or modification parameter, as I said, can be determined or estimated in many different ways. But the main principle for all of them is this, that you have to compute them, insert them back into the modified kernel.